Okay, so last lesson we looked at this sort of examples where something was going down a hill and you were sort of being asked to use a change in the potential energy to work out the kinetic energy gained. So if it starts off here and you work out this has got a potential energy of, say, maybe 1,000 joules, and this might be 60 metres high, the question might be, how much kinetic energy does this have here? Actually, there's two questions you'd be asked. One could be the potential energy here at maybe 40 metres, and one could be the kinetic energy at 40 metres. So in terms of potential energy at 40 metres, you could normally go through and do this again and put in your 40 as your value for H. But the reality is, this has actually gone through, it's still 40 out of 60 above the actual ground here. So it's 40/60ths of the original, or 4/6 or 2/3 of the original. So that's what you don't have to do. The quick way is it's 2/3 of the original value, because it's 2/3 the height, so you would do it as 2/3 of that value there. Okay? So that's one way of doing it. The kinetic energy here, though, is based on the potential energy it's fallen through or lost here, based on the height it's fallen through. And it's fallen through 20 metres out of the 60. So if you look at it that way, it's gone through 20 out of the 60. So it's gone through 1/3 of the original. Okay? So you could do that as 20/60ths of 1,000. So that's a way of working out the kinetic energy. You look at how much it's fallen through as a fraction. Okay? The other way of doing that, to find the kinetic energy, is look at the potential energy lost. In which case you're going to do the original, which is 1,000 joules, minus potential energy it's got at this point here. Okay, so if you were doing that, this would be 0.67 of that, so you've got 667 joules. Okay, here you would have about 333 joules roughly. So you would say, okay, this has actually fallen through and lost, this has actually got a potential energy to start with of 1,000. It's now got a potential energy of only 667, so you would take off the 667 and you're roughly getting 334 joules of kinetic energy. So either you would do it as a fraction, which is the quick way, look at how much of a fraction has gone through and turned into kinetic, or you could actually say, okay, well, it's going to be the potential energy lost, which is the original, minus what it's got left over at the moment. And both way methods will get it for you. All right. Now let's just look at some examples here of what happens if it's at an angle. So if the force is at an angle, force at an angle. So here what we've got is you've got a person pushing a lawnmower, so they're going to exert a force down the panels here. So that's the force. All right. So let's say that's 100 newtons, just to make it easy. It'll be more than that actually. And we're going to move the lawnmower a distance of maybe 10 metres in one line. And we're going to form an angle here with the ground of maybe 40 degrees. So according to that, they've got to be the force and the distance in the same direction, or displacement in the same direction. Now looking at that, this force is acting like this. We're interested in the forces acting in this component here, that way. Okay? So how do you work out what that force component would be based on that angle? So if you go back to sort of work with projectiles, that's the cosine component there, because it's the adjacent side compared to the hypotenuse side. The cosine of 40 would actually be the adjacent side that they're trying to find, x here, over the hypotenuse side, the force. All right? So you can see here that what you're actually going to do here is going to work out that x is f cos 40. All right? So x will be f cos 40. Cosine of 40. Now, that's why the formula, when you look at it then, in general is not written as fs. It's written as fs cos theta to remind people that they've got to be going in the same direction. If they're not, the cosine theta will normally give you the force component that's parallel to the displacement. So looking at that here, you could just substitute it straight in there rather than actually go through all this sort of hassle for those who don't like doing trig. Then we'll do that. We can say, well, the force here down the handles is 100 newtons. The displacement of the lever is 10 metres. And the cosine of the angle that it's making here with the ground is 40 degrees. And that will give you the work done and the change energy in one go. So what we're going to get here is 766 joules. Okay, so 3 significant figures, which is probably too many. So that's one way of doing that one. All right. Now if you do the same sort of thing with the questions where it's like this, it could be a dragging question instead, where they're dragging something there, and the tension down that rope then, the force of tension might be 200 newtons. Okay, and then they're going to make an angle here, let's say 30 degrees with the ground, and we're going to move the person here and drag her 10 metres on a flat slope there, so this is before it goes up the slope. And again, you're just quickly going to go work equals Fs cos theta. So this is F times by S times by cosine of theta. The force that's at the tension down the rope here, that's at an angle, is 200 newtons. But that'll be the cosine of 30 to work out the component in this direction, the same direction as it's going, and it's going to travel 10 metres. So putting all those ideas together, you're going to get an answer there. And you could round that off to so many significant figures. Let's say it's 1.7 by 10 to the 3 joules to 2 significant figures only. Okay? So that's the idea of those sort of questions.